so there would not be a kind of disturbance.
Ma'am, can I start now?
Yes, definitely you can.
Okay, so hello to my all of friends. Am I audible to you all?
Yes,
Yes, yes.
yes, Aryan.
Okay, thanks a lot,
Yes.
my dear
Yes,
friends. Let's
sir.
start this topic. So today I'm going to talk you about the introduction of superconductivity. Friends, my screen is visible to you all or not?
Yes,
Yes, it is
visible.
visible.
Yes, so friends,
Yeah.
let's have a great time. So friends, first of all, I'm showing the logo of the LD College of Engineering. I don't need to tell you what is it. It is the greatest organization, greatest institute of the Gujarat, and in my opinion, it is the greatest of world. So I'm going to start with it. I'm very lucky to be a part of it, and we all are lucky to be a part of it. So let's start the topic, introduction of superconductivity. But before starting, I would like to give a special thank you to respected Vaishali Advaryu ma'am, to respected Jignesh Hirpara sir, and to respected Hiral ma'am, who are always supporting us, who are always helping us in all over the things. And I think you all are knowing me. So by this detail which I given about me, you will know me very much preferably. So I think this is my detail. You know about me. Okay, students, so let's start today's topic. Friends, here you can see a picture of an old man. Friends, he is a H.K. Owens. Friends, H.K. Owens was the first person who had discovered this superconductivity. Friend, how he had discovered? Friends, one day in 1911, the H.K. Owens was doing a practical in which he had put a piece of mercury which is highly resistive in liquid helium. Liquid helium is staying on a temperature of 4.15 Kelvin. By putting the piece in the liquid helium, H.K. Owens noted that the resistance of mercury gone to the zero. The resistance of mercury becomes zero. It was zero. That's why H.K. Owens was thinking that how it is happening, because of it was totally unexpected with the rules of physics. Physics is telling that every of the thing is related with such kind of resistance, because we all are knowing there are three type of things: conductor, semiconductor, and superconductor. Of course, friends, conductors, semiconductors, and superconductors. Conductors are the thing which are helping you to transfer the current from each part to second part, which allows you to flow the current from it. It is the conductor. Semiconductor you better know. And this is the superconductor which HK Owens found. How he had found? He had noted that by putting the mercury piece in the liquid helium at 4.15 Kelvin, it the resistance of it goes to the zero. It goes to the zero. That's why he has said that mercury regained its resistivity after heated it above. Means, are you getting? Let me tell you in Gujarati also, so that it would be more preferable you. 1911 માં એચકે ઓન્સે એક પ્રેક્ટિકલ કર્યો કે જેની અંદર તેમણે મર્ક્યુરીના એક ટુકડાને લિક્વિડ હિલિયમની અંદર મૂક્યો. લિક્વિડ હિલિયમ કે જેનું ટેમ્પરેચર 4.15 કેલ્વિન, જો આપણે આને સેન્ટ્રી સેલ્સિયસમાં ટ્રાન્સફર કરીએ તો -270 ડિગ્રી, -270 ડિગ્રી જેટલા ઠંડા ટેમ્પરેચર ઉપર મર્ક્યુરીના પીસને લિક્વિડ હેલિયમમાં મૂકવામાં આવ્યો, તો મર્ક્યુરી કે જે હાઈલી રેઝિસ્ટિવ છે તેનું રેઝિસ્ટિવ ઝીરો થઈ ગયું, જે ક્યારેય પણ ભૌતિક વિજ્ઞાનના નિયમોમાં આવતું નહોતું. એન્ડ ઇટ વોઝ ફર્સ્ટ ટાઈમ ઇન ફિઝિક્સ. બીકોઝ ઓફ આપણે વાહકો અર્ધવાહકો ભણ્યા છીએ, તેની અંદર કોઈક ને કોઈક રીતે રેઝિસ્ટન્સ હોય છે. ઇટ ઇઝ અ ડિફરન્ટ થિંગ કે તે લોકો થોડાક પ્રમાણમાં તો રેઝિસ્ટિવ હોય જ છે, but and they are giving you some allowness to flow the current. So they are giving you the allowness to flow the current, but also they are having some kind of resistivity. But mercury ની અંદર resistivity zero થઈ ગઈ હતી, જે વસ્તુને એચકે ઓન્સે નોટ કર્યું. પછી એચકે ઓન્સે તે મર્ક્યુરીના ટુકડાને ગરમ કર્યો અને ગરમ કરતાની સાથે ફરીથી મર્ક્યુરીના ટુકડાએ પોતાની રેઝિસ્ટિવિટી પાછી મેળવી લીધી. આ વિચિત્ર પ્રકારની ઘટનાને એચકે ઓન્સે સુપર કંડક્ટિવિટી નામ આપ્યું. એમણે કહ્યું કે એક સર્ટેન ટેમ્પરેચર ઉપર કે સર્ટેન ટેમ્પરેચરથી નીચે જતા મર્ક્યુરી પોતાના રેઝિસ્ટન્સને ઝીરો કરી નાખે છે. મર્ક્યુરી તેના રેઝિસ્ટન્સને ગુમાવી દે છે અને પાછા ટેમ્પરેચર સુધી લઈ જતા તે પાછું રેઝિસ્ટન્સ મેળવે છે. So friends, if you are going in on Google, or if you are going on any website and you are finding the superconductors, you can see this type of images. They are using this type of images in which the piece of superconductor is having such kind of vapor. which is cold vapor. Why it is? Because of normally superconductors are available in very low temperature. Superconductor બહુ નાના ટેમ્પરેચર ઉપર જ અવેલેબલ છે, નિયરલી -270 થી નીચા ટેમ્પરેચર પર. ફ્રેન્ડ્સ, આ બિહેવિયરને એક્સપ્લેન કરવા માટે એચકે ઓન્સે ધ ગ્રેટ ગ્રાફ રેડી કર્યો, જેની ઉપરથી તેમણે આ બિહેવિયરને સમજાવ્યો હતો કે વોટ ઇઝ ઇટ, વાય ઇટ ઇઝ હેપનિંગ ટુ અસ, why it is happening to us. So friends, you can find that this here is two graph. One of red graph is superconductor and blue graph is normal metal. Friends, at high temperature, normal metal is also having the high temperature. Normal metal is also having high resistivity, but at zero temperature or less than zero, it is having certain. It is not having zero. It is having certain value. But in superconductor, you can find at this point. You can see my arrow. At this point, the resistance in superconductor directly goes to zero. Not gradually, it goes directly. Not gradually, it goes directly. Just in a sudden, it becomes zero without taking any time. Just coming on that point, it goes zero. So it was the unexpected phenomenon which was called superconductivity by H.K. Owens. ફ્રેન્ડ્સ, સુપરકન્ડક્ટિવિટીની આ જ ઇશ્યુ હતી કે તેઓ સુપરકન્ડક્ટર્સ જે હતા તે એક બહુ જ નીચા ટેમ્પરેચર પર વર્ક કરતા હતા. It is a different thing that we found some more superconductors, lead, zinc, aluminum. You can find these lines also. I have noted. You can see. Here are the some words: lead, zinc, and metals, and thousand number of alloys. ઘણી બધી મિશ્ર ધાતુઓ પણ છે, હજારોના પ્રમાણમાં મિશ્ર ધાતુઓ એવી છે જે સુપરકન્ડક્ટિવિટીનો ગુણધર્મ ધરાવે છે. ફ્રેન્ડ્સ, 1980 સુધીમાં આટલા ઘણા બધા શોધાઈ લેવામાં આવ્યા હતા. બટ ધ મેઇન પ્રોબ્લેમ વોઝ ધેટ વી કાન્ટ યુઝ ધીસ મચ ટેમ્પરેચર ઇન આર નોર્મલ લાઈફ. નોર્મલ લાઈફની અંદર આટલા નીચા ટેમ્પરેચર સુધી જવું નિયરલી ઇમ્પોસિબલ છે. And we want to use superconductors in our life. So it was very typical, but we found a solution for that. Friends, you can notice certain type of ceramics are there. Certain type of ceramics are there. These are the certain ceramics which are exhibiting their superconductivity at temperature 120 Kelvin. They are exhibiting their superconductivity at temperature 120 Kelvin. 120 કેલ્વિન ટેમ્પરેચર સુધી પણ તેમ પોતાની સુપરકન્ડક્ટિવિટી શો કરે છે. તો તેવા સિરામિક પદાર્થો પણ આપણને મળ્યા છે. So it is helpful for us now. Now we can use it. Otherwise -270 degree આપણા normal life માં it is never possible. In certain kind of things possible, but in a giant way it is not possible. We can't use in our atmosphere. We can use in a isolated form, right? We can't use in a open area, or we can't use in a open atmosphere. So friends, હવે જે HK ઓન્સે જે વસ્તુ નોટ કરી હતી કે કોઈ એક સર્ટેન ટેમ્પરેચર છે કે કોઈ એક સર્ટેન પોઈન્ટ છે કે જ્યાં જતા ડાયરેક્ટલી જસ્ટ ઇન અ સડન ધ રેઝિસ્ટન્સ ગોઝ ટુ ઝીરો. સો એને ડિફાઇન કરવા માટે તેમણે એક ગ્રેટ વર્ડ લીધો છે, ટ્રાન્ઝિશન ટેમ્પરેચર. Friend, if you are going to the reference books, you can have two different type of words: transition temperature and critical temperature. Both are there. You can use any one of them. In some of the book like Atul Prakashan and Pearson, they are using critical, and S. Chand using transition. So I have preferred both words so that I can give you some more introduction about it. So the temperature at which a normal material abruptly changes into a superconductor is called transition temperature. Friends, as per I said, it happens abruptly. એક ઝટકામાં થઈ જાય છે, એકાએક થઈ જાય છે. It happens abruptly in sudden. That just in a sudden it converts its resistance from a high level to zero level. And the point on which it happens, જે પોઈન્ટ ઉપર આ ઘટના બને છે તે પોઈન્ટને ટ્રાન્ઝિશન ટેમ્પરેચર, ક્રિટિકલ ટેમ્પરેચર કહેવામાં આવે છે, and it is denoted by TC. Though I was writing in a WordPad, so that they are not allowing me to use the C as a suffix. So I haven't denoted the C as a suffix, but you can find that C is suffix in with T. It is the TC temperature, you can say. And also I have added this word so that I can give you more of idea that it is a critical temperature. It is also known as a critical temperature. So you do not have to worry. Transition temperature, critical temperature, both are the same things. Let's go ahead. Friends, now I'm going to talk about the materials. Friends, since the discovery of superconductivity in metal mercury, જ્યારથી આપણે લોકો mercuryની અંદર આ જે superconductivity શોધી છે, friends, we started to found more and more because of the superconductors were having a different kind of property which was very much useful. Friends, one of you, I would like to ask you, friends, that if I'm going to convert the resistivity at zero according to Ohm's law, V is equals to I by R, what will happen? Anyone can reply? What will happen? Just think, in the equation of V is equals to I by R, you are going to V is equals to IR, you are going to put the value of R with 0. What will happen with I? What will happen to the equation? Anyone can tell me?
Current will tend to infinity.
Yes.
Perfect. Perfect. It is said by that કે જ્યારે તમે આવું કરશો કે રેઝિસ્ટન્સ ને 0 કરી નાખશો તો કરંટ ફૂલ પાવરમાં મીન્સ કે કરંટ ઇન્ફિનિટી પાવરથી વહેવા લાગશે. There will be nothing anything which will oppose you because of Ohm's the scientist Ohm who have found the resistance. Ohm से आज કહ્યું હતું कि certain type of property is there which is opposing the current to flow. What is resistance? Resistance is one kind of property which is opposing the current to flow, but whenever you are going to make the resistance 0 without applying any voltage, superconductor will have certain current. Great. Without connecting with battery, you will have current. It is said by HK Owens and the scientists which have studied about it. So friends, after that we started to study more and more about the superconductors because of it was a interesting topic for all of us. Physics ની દુનિયામાં એક નવું startup કહી શકો છો. It was a new startup in physics that we are having certain type of things. So we started to do study on it and we found about 40 elements from our periodic table. I have noted this from here for you. It is most time in MCQ. If MCQs are coming into the examination, may it will be IMP for us. That 40 elements we found from periodic table which are exhibiting as a superconductors. Friends, not only this, apart from this, we have thousands of alloys. હજારોથી વધારે મિશ્ર ધાતુઓ છે અમારી પાસે કે જે આવી સુપરકન્ડક્ટિવિટી બતાવે છે. Friends, I thought that I am going to give you the great topic and I will try my 100%. So definitely you would be interested in this chapter. So that I have added some external concepts also. So it was just for the GTU, whatever I have told to you. Now I'm going to tell you some external concepts which will help you to understand more about it. So friends, in the same thing, one is given here that the type of superconductors. Friends, there are two types of superconductors. One is type 1, second is type 2. Friends, type 1 superconductor ની અંદર આપણે elements લઈએ છીએ. Like you can take 40 elements which I said to here. Here is the 40 elements. These 40 elements are coming in type 1 superconductors, and the alloys એટલે મિશ્ર ધાતુઓ, જે મિશ્ર ધાતુઓ તેમાંથી બનાવવામાં આવે છે તે મિશ્ર ધાતુઓ માટે આપણે type 2 રાખ્યો છે. Friends, the great thing which you should note, friends, જ્યારે type 2 ની અંદર મિશ્ર ધાતુઓ કે alloys ની સાથે આપણે superconductor બનાવીએ છીએ, sometimes it happens that એમાંથી કોઈ એક સુપરકન્ડક્ટર હોય તો પણ ચાલશે, બંને સુપરકન્ડક્ટર હશે તો પણ ચાલશે, અને બંને નહીં હોય તો પણ ચાલશે. Yes, it is happening. If I am going to talk about the CUS, friends, CUS, it is cupric sulfide. Friends, cupric sulfide ની અંદર copper પોતે એક કંડક્ટર છે. Though it is a good conductor, it is not a perfect conductor like superconductor, but it is a good conductor. We are using it. Normally, તાંબાના વાયર આપણે જોયા છે. So it is a good conductor which we are using. And sulfide I don't find as a conductor. So both are not superconductor. આ બંને superconductor નથી. પણ આ બંને ભેગા મળીને superconductive મિશ્ર ધાતુ બનાવે છે. So that's the thing which we should note. This is the notable thing કે both are not superconductor, but both are making certain superconductor. જ્યારે બંનેની મિશ્ર ધાતુ રેડી કરવામાં આવે છે ત્યારે બંને સુપરકન્ડક્ટર બને છે. Friends, so superconductivity is still an exciting field of discovery and technological application. Of course, friends, when we found about the gates and when we found about the AND gates, NAND gates, about that gate and semiconductor, we have started a great thing. I have one thing to tell you, friend. Gargan Murray. Friend, there was a great scientist, Gargan Murray. Friend, Gargan Murray has said that કે જેટલી સ્પીડમાં સેમિકન્ડક્ટરની દુનિયામાં પ્રગતિ થઈ છે, જેટલી સ્પીડમાં સેમિકન્ડક્ટરની દુનિયામાં પ્રગતિ થઈ છે, તેટલી સ્પીડમાં જો ઓટોમોબાઈલમાં પ્રગતિ કરવામાં આવે ને તો રોલ્સ રોય કાર 1 લિટર પેટ્રોલની અંદર 50,000 કિલોમીટર ચાલશે અને પછી તેને પાર્ક કર્યા વગર તેને ફેંકી દેવી સસ્તી પડશે. ફ્રેન્ડ્સ કેન યુ બિલીવ જેટલી સ્પીડમાં સેમિકન્ડક્ટરની દુનિયામાં પ્રગતિ થઈ છે એટલી સ્પીડમાં જો આપણે ઓટોમોબાઈલની અંદર પ્રગતિ કરશું તો આપણી રોલ્સ રોય કાર 1 ગેલન 3 લીટર પેટ્રોલની અંદર 50,000 કિલોમીટર મૂવ કરશે અને એની પછી એને ક્યાંક મૂકી દેવા કરતા એને ફેંકીને નવી બાય કરવી સસ્તી પડશે. It was said by Gargan Moore and it was very much famous into the world of semiconductor. Semiconductor ની દુનિયામાં ઘણું famous word છે, sentence છે, Gargan Moore sentence for the development of semiconductor. Friends, semiconducting magnets are the powerful electromagnets. We all know, friends, we have heard about the maglev train. Even we are going to take in India also. So I will tell you about it just in a next paper. First I want to complete the all over the benefits which we are having it now. So first of all, MRI and NMR machines, in them we are using superconductors. In mass spectrometer we are using superconductors. Beam steering magnets are using in superconductors. Particle accelerator ની રીતે વાપરીએ છીએ આપણે. Digital circuits જે rapid single flux ની ઉપર quantum technology માં base થયેલી હોય છે કે જેનો આધાર rapid single flux quantum technology છે એવી digital circuits and RF microwave filters mobile phone, they all are working on superconductors. Friends, superconductors are used in direction to build Josephson junction, which are the building blocks of squids, and squids means superconducting quantum interface devices. Okay. Even friends, I have taken some pictures for you so that I can give you some more detail that what I want to convey to you so that you can get me properly. So first of all, this is the MRI scanner cutaway. Yes, friends, this is the MRI scanner and I have labeled everything whatever was needed. Here is everything is labeled for you, that this is the radio frequency coil, this is the gradient coil, and you can find a superconductor right here also. Friends, this is the circuit which are mostly and highly using and majorly which is using in the EC department. Electronic communication, in them we are using a lot. What is it? It is a circuit. And now AMD and Nvidia type of companies, they are doing a different and a great development on it. If you are going to compare the earlier computer science with today's computer science, it is developing very rapidly. You can't count the speed. કોમ્પ્યુટર સાયન્સની અંદર અત્યારથી 10 વર્ષ પહેલા જ્યાં 12 થ્રેડની સર્કિટ મળવી અઘરી હતી, અત્યારે 40,000 થ્રેડની સર્કિટો આવી રહી છે. So it is the great development in computer science and which is happening by AMD, Nvidia, Ryzen, this type of companies which are doing this. And in India, the Bangalore is also known as Silicon Valley. So friends, we have already done a great development in the direction of semiconductor, and now we are going to done a great development in superconductor also. Friends, some certain examples are here. I have taken this example for you because of I think that it can tell you more properly. Friends, जो સેમિકન્ડક્ટરની દુનિયામાં સેમિકન્ડક્ટર કે જે અર્ધવાહકો હતા, with only them we have did this much development. So now we are having superconductors. So you can think that if we are working on it, we will have super development. We will have a different physics direction on the earth. Now friends, it is the transportation where we use. In Japan, it is using a majorly level. And now it is more safe in comparison or of our train. જે ટ્રેન પાટા પર ચાલે છે કે the trains which are going with wheels, the trains which are going with wheels, in comparison with them, it is more safe. It is more safe, the maglev train, because they cannot jump or they cannot take out from their way. Okay, so first of all, you can find it here also. Yeah, it is given it here, superconducting magnet on board. Friends, for that I have given this one picture. It can explain you more deliberately. It can explain you more deliberately. ટ્રેનની અંદર જે ટ્રેન યુઝ થાય છે તેની અંદર બી બે મેગ્નેટ્સ હોય છે N and S. તેની અંદર પણ બે મેગ્નેટ્સ હોય છે N and S. Even though they are superconductors, they are not magnet but superconducting magnets. They're superconducting magnets. Even also on the way on which train is moving, you can see in both pictures. You can see in the both pictures it is going in comparison, it is going with simultaneously with help of both. If you are zooming this picture, you can find that N and S constantly simultaneously use of their attraction and distraction, they are doing this. with the use of distraction and attraction, they are doing this, which is helping you superconducting magnets. And friend, with this great innovation, we made a train which can move 603 kilometers per hour. It is the maglev train which is moving in Japan. Friend, 600 kilometer per hour. India's longest route is 700 to ઇન્ડિયાનું લોંગેસ્ટ રૂટ છે જે ઇન્ડિયનની ટ્રેન 3 ડેઝમાં કમ્પ્લીટ કરે છે 7200 કિલોમીટર. યુ કેન કમ્પ્લીટ ધેટ રૂટ ઇન ઓનલી 12 hours. જે રૂટ કમ્પ્લીટ કરવામાં ઇન્ડિયન ટ્રેન્સ 3 થી 4 દિવસનો ટાઈમ લે છે એ રૂટ ઓનલી 12 hours ની અંદર કમ્પ્લીટ થશે જો આવી ટ્રેન ઇન્ડિયામાં આવે તો. And which kind of train it is? It is the maglev train. It is moving on superconductive principles. It is the superconducting principles, superconducting magnets principles it is moving on. And friends, so finally I have told you this much thing about superconductors which is working this much. But friends, the every innovation which happened is starting with this. The everything which has happened to us, the everything what we got is started from here. The great person HK owns. HK owns na great experiment થી આજે આપણને superconductor મળ્યા છે. So friends, at last we are greatly thankful of Dutch physicist HK owns for giving this wonderful gift to us. We are always be thankful of HK owns. Friends, HK owns has awarded Nobel Award for his low temperature discovery in 1913. 1913 માં HK owns ને તેમને નોબેલ એવોર્ડ મળ્યો હતો લો ટેમ્પરેચરની ડિસ્કવરી માટે કે લો ટેમ્પરેચર ઉપર જે રેઝિસ્ટન્સ સાથે ઇફેક્ટ થાય છે તેની માટે. ઇવન ફ્રેન્ડ્સ, યુ હેવ હર્ડ 12th ની અંદર સ્પેશિયલ એક્ઝામ્પલ્સ આવતા હતા રો 0 માઇનસ r1 માઇનસ r2 બાય alpha r1 is equals to t1 minus t0. Friends, a b resistance and temperature વચ્ચેનું રિલેશનશિપ હતું. Still HK owns has discovered something different. HK owns has discovered about the less temperature, about the low temperature, not about the high temperature. So for this discovery he got the great award in the direction of in the world of physics. Physics na world ma સૌથી મોટું award છે Nobel Award, which he got in 1913, which he got in 1913 for the discovery of low temperature. In 1913 he got. And friends, again I'm a great thankful and thank you very much to the respected Vaishali ma'am, to the respected Jignesh sir, and to the respected Hiral ma'am, who are always very much supporting to me, who are always very much helping to us. Thank you very much. We are very much lucky for having these great teachers to us. Thank you very much, ma'am. Any one of you is having any kind of doubt, and if I forgot to convey something, please remind me. Please kindly, gently remind me.
Aryan, together we grow. है ना Aryan?
Yes, ma'am.
Very energetic and very powerful presentation, Aryan. I hope everybody liked it. I hope everybody could get the thing you wanted to convey. Very powerful. Very nice.
Yes, ma'am.
Right? Yes.
Thank you
Clappings
very
are
much.
for you. I've started having, I've started showing you in terms of, yes, great round of applause for you. Very nice. Very nice. મજા આવી બધાને છોકરાઓ? Have you enjoyed?
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Have you
Yes, ma'am.
have you got the
Definitely,
content
ma'am.
that he was delivering?
Yes, ma'am.
Right? અને હંમેશા આર્યને બધાને એડ્રેસ કરતો તો he was keep on telling you friends does mean together we grow. હે ને? Superb. I would say it's a superb, Aryan.
Thank you very much, ma'am. Each word is very much invaluable. Thank you very much.
It is always there. When you are doing something good, we have to motivate. This is our main role. Right? ભણાવવા માટે તો books પણ તમારી પાસે છે. હવે તો we have many resources. But still, motivation or the things which you have, that should come out. Right? Okay, fine. એક વખત ફરીથી slide માં આવી જજો. Is anybody does anyone have any kind of question, friends? Does anyone have any kind of question? You can ask to Aryan first. Aryan માટે કોઈ પ્રશ્ન છે?
Yes, I can ask something.
Yes, definitely you can ask to Aryan. No issues. Aryan has kept the session open for everybody. Open session means you can ask Aryan.
But I want to discuss that.
I'm not getting because
I'm not asking anything, but I want to discuss that when resistance is 0, then voltage becomes 0. Then how current will flow in a conductor? If voltage is
yes,
tending to 0.
Aryan, this question is for you. He is asking that if resistance is 0, how current would flow? This much I could get because there was a cracking in voice.
Yes, resistance will also become 0.
Okay.
If resistance is 0, then voltage becomes 0. Then how current will flow in a conductor? Superconductor.
Yes. Aryan, I hope you understood the question now.
Oh, sorry, ma'am. My mic was off.
Continue.
Yes. Can you see my screen, friends?
Yes.
Yes, everybody can see the.
Yes.
Okay, friends. So I have written the Ohm's law. Friends, whenever you are putting the value of R in it, it becomes V is equals to 0. It shows that only I is left. Everything becomes 0. Only I is left. So the things which will happen કે જે કંઈ પણ થશે તે V ની 0 value પર થશે. So it is coming from the Ohm's law, but I don't have a I don't have experimented that how it is happening. But the law of Ohm's law is telling that there should be current by auto generated with the properties of superconductors because of આપણે રેઝિસ્ટન્સ ની વિશે જ્યારે ભણ્યા છે ત્યારે આપણને ખબર છે કે રેઝિસ્ટન્સ ઇઝ સચ કાઇન્ડ ઓફ થિંગ કે જે કરંટને ઓપોઝ કરે છે, રાઈટ? એટલે કે રેઝિસ્ટન્સ કરંટને ઓપોઝ કરીને ઝીરો કરી નાખે છે, રાઈટ? બટ જ્યારે રેઝિસ્ટન્સ રહેશે જ નહીં તો કરંટ ત્યાં હશે. ઇવન સર્ટન કાઇન્ડ ઓફ થિંગ્સ આઈ કેન સે દેટ we are noting it in winters ની અંદર our great teacher Vaishali ma'am has already explained that in winters we are noting that whenever we are using the blankets we are hearing some kind of voice chat type of voice we are hearing, right? Anyone heard? Anyone noted?
Static current.
It is such kind of current which is coming to us without any voltage. We are not connecting it with the battery, but it happens. So it is happening in conductors or non conductors which are જે અધાતુઓ છે કે જે કંડક્ટર્સ છે જ નહીં તેની અંદર બી આ હરકત થાય છે. So if it is happening into them, so what can you think about them which are having no resistance કે જેની અંદર રેઝિસ્ટન્સ જ નથી તેનો કરંટ કેટલો પાવરફુલ હશે? So it can happen like that.
Very good try, Aryan. Very good try. But I would like to add something in that. Very nice try. The way you have explained is amazing. Fine. You have used your knowledge by which you have explained it. Okay, kono prashna hato? Please raise your hand. Who has this question?
No, ma'am, I don't have question. I only want to discuss this topic.
Yes. I totally understand. Don't worry, Suraj. We are here to discuss. Don't worry. And don't feel bad. If you have a question, you are most welcome. Yes. Suraj, let me tell you one thing, that whenever we are using superconductor in any of the practical application, it has always a loop form. Can you see a loop? Can you see my video?
Yes, ma'am.
You see? It's a loop. previously when we were using PN junction diode, Zener diode, they are all semiconducting material. But in that particular, Aryan, you keep on showing us presentation.
Okay, ma'am. Thank you.
You keep it on only. Yes. So previously when we were using PN junction diode, we have so many components present in the circuit. Am I right? We have started with battery, we have resistor, we have potentiometer, we have diode, we have current meter, we have voltmeter. Am I right, everyone?
Yes, ma'am.
Okay, so
Yes,
many
ma'am.
components are connected either in series or in parallel. But when we talk about superconductor, when we talk about temperature which is less than critical temperature, the material shows you superconductive nature. At that time, the material is not connected any other component. It has its own loop form, this kind of loop form. We have to initiate current in that, either with the electric field or with the magnetic field. Aryan, here is the correction. Fine. We have to definitely initiate current in the material. Then you can take off the source. Okay. Because it is in superconducting state, there is nothing to oppose. Rightly you said. There is nothing to oppose. Does mean, do you think voltage drop will come? Voltage drop thashe?
No, ma'am.
No, ma'am.
No, ma'am.
No, voltage drop, can I say it is a kind of energy drop?
Yes, ma'am.
No, ma'am.
Is it a kind of energy drop?
Yes, ma'am. Between 2 points, it is a kind of energy drop.
Yes.
Yes, it is an energy drop. Energy drop ક્યારે થાય તમારી? Energy ક્યારે drop થાય? Tell
Voltage
me.
difference.
No, energy
When there
drop
is a
ક્યારે?
potential.
No.
When does someone
Potential.
put the energy? Hindrance હોય.
Yes, when some parameter is present which opposes the motion, then there will be an energy drop. Understood? Energy
Yes, ma'am.
drop થવા માટે resistance no factor જોઈએ. But in our case, in this superconducting state of a material, there is no chance of resistance. Due to that, there is no energy drop. Due to that, there is no I square R loss. Due to that, current would be infinitely move on and on in a given loop. આ જે loop માં initiate કરી દીધો છે current, એમાં એ continuous flow કરશે until and unless any condition t less than tc જ્યાં સુધી satisfy રહેશે ત્યાં સુધી. When t greater than tc, the material will turn into normal state and there would be a kind of appearance of resistance. Suraj, understood?
Ma'am, repeat the last sentence when energy drops if it's any bar.
Yes, I was telling that when material is having T less than Tc, suppose I'm talking about, let us say lead, PB, plumbum. PB ખબર છે ને બધાને? Which is used for shielding purpose. Nuclear reactor માં shielding માટે PB નો use થાય છે. Plumbum
Yes,
sisu.
ma'am.
Yes,
Right?
ma'am.
Yes, PB નું TC છે 7.3, 7.4 Kelvin. Plumbum. હવે I am now keeping the temperature of plumbum less than 7 Kelvin. So have I satisfied the condition T less than Tc? Okay, na? Have I satisfied the condition T less than Tc? I've kept temperature 7 Kelvin.
Yes, ma'am.
Yes, ma'am.
नहीं 7 Kelvin. Yes.
Clear? આગળ વધુ હું?
Yes.
Yes,
Fine.
ma'am.
Yes.
Now by this condition I am using or I am framing a loop in which I want to initiate current in plumbum, either with the electric field or with the magnetic field. બેમાંથી કોઈ પણ રીતે હું current એમાં initiate કરી શકું. Electromagnetism word બધાને ખબર છે, હા કે ના? इलेक्ट्रोमैग्नेटिज्म.
Yes, ma'am.
है ना? So when you are thinking of electric field, there is inherently a presence of magnetic field always there. It is vice versa. એટલે magnetic field હોય ત્યાં electric field હોય ત્યાં magnetic field. Do we know it very well?
Yes, ma'am.
Yes, ma'am.
Both are interrelated.
So I have initiated current in that way. પછી મેં સોર્સ ને કાઢી લીધો બહાર, કેમ કે મારે લૂપ બનાવવાની છે. સુપર કન્ડક્ટિંગ મટીરિયલ હંમેશા લૂપ ફોર્મમાં જ યુઝ થશે, એની સાથે બીજો કોઈ કમ્પોનન્ટ એડ નહીં થાય. ધ રીઝન, બીજા કમ્પોનન્ટ નો રેઝિસ્ટન્સ હશે. Due to that there is I square R loss. Due to that there is heat dissipation. Due to that T will be greater than TC. Got it everyone?
Yes, ma'am.
So yes, no other regular components, no other regular metal or semi-metal or insulator can be kept with the superconducting state of a material. હવે in that loop current initiate કરી લીધો છે. Suppose I have set 1 ampere current. How much I have set in the loop? લૂપમાં મેં કેટલો કરંટ સેટ કર્યો?
1 ampere.
1 ampere.
1 ampere. એ એની જાતે નથી થયો હો. I have set into it. Fine. 1 ampere current में
Yes.
set करियो. Now due to lattice formation, due to phonon interaction present in the superconductor, એ આગળ આવશે, આગળના ટોપિકમાં આવશે. લોઅર ટેમ્પરેચરે અંદર જે મટીરિયલના ઇલેક્ટ્રોન્સ છે, કુપર પેર છે, પેર ઓફ ઇલેક્ટ્રોન્સ છે, એનું ફોર્મેશન થાય છે. ડ્યુ ટુ ધેટ રેઝિસ્ટન્સ ડઝન્ટ અપિયર ઇન ધેટ સ્ટેટ. રેઝિસ્ટન્સ રહેતો જ નથી. કરંટ એટલે જે dq by dt છે, dq by dt એ constantly, let me tell you, constantly it will provide 1 ampere current at least for 10 to the power 6 years as it is. No decay is recorded in that. समझ पड़ी बधाने? Infinitely doesn't mean કે 1 ampere will become 2 ampere. એક વર્ષ પછી 2 ampere થશે, પછી 10 ampere, 100 ampere. Not in that way infinitely. Infinitely in terms of time parameter. Infinite time સુધી જે કરંટ સેટ કરેલો હતો 1 ampere, that would last as it is. Is that fine? Everybody understood?
Yes, ma'am.
Means, ma'am, we can store energy in superconductor and we can use it when we need.
We can store, energy cannot be stored. It is continuously
Means, ma'am,
showing.
current.
We can use, definitely we can use. Yes. પણ એ સ્ટોર એનર્જી કરવા માટે એક વસ્તુ વિચારો તમે. compressor has to I mean the main system coolant.
Yes, ma'am, we need more coolant and
yes, coolant ના ભોગે આપણે એનર્જી સ્ટોર કરીએ છીએ. એટલે એનર્જી સ્ટોરેજ નો ઓપ્શન એમાં નથી. We can use it whenever it is needed. અને આપણને બધાને ખબર છે, when somebody wants to work with lower temperature, આપણી પાસે બે હોમ એપ્લાયન્સીસ એવા છે કે જેમાં જે ટેમ્પરેચર ઘટાડે છે. નામ આપશો મને? Two home appliances nowadays we all have. What are those two?
AC and refrigerator.
એનું હાર્ટ કેશો, એનું હાર્ટ જેવું મશીન કયું છે કે જેનાથી આપણને ચિલ્ડ એટમોસ્ફિયર મળે છે?
compressor.
Condenser. Yes, compressor and condensation. Okay, compressor is the one by which air is being compressed. Compressed air થાય એટલે એ શેમાં ટર્ન થાય? Liquid. ઓકે, એટલે જ હિલિયમ છે, નાઇટ્રોજન છે, એમાં શબ્દ વાપરે છે liquefied helium, liquefied nitrogen, because compressor is used. એટમોસ્ફિયર નો નાઇટ્રોજન અથવા એટમોસ્ફિયર નો હિલિયમ, concentrated helium નાઇટ્રોજન ના બોટલ એને liquefy કરે. That can be done by using compressor. Okay everybody? Anyone has any confusion now?
No, ma'am.
No. Yes, are you all clear with the topic introduction to superconductors?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
ઓકે ફાઇન. આર્યન તમારી જે પીપીટી છે એ પીપીટી ગ્રુપમાં શેર કરજો, બરાબર? તમારા ગ્રુપમાં શેર કરજો, હા ને? અને આ પીડીએફ જ શેર કરજો, બરાબર? એમાં બધું વ્યવસ્થિત ડિટેલ ને બધું આપેલું છે, સો ધેટ વુડ બી અ ગુડ રેફરન્સ ફોર ઈચ એન્ડ એવરીબડી. ફાઇન, થેન્ક યુ સો મચ આર્યન. ફરીથી કહીશ કે બહુ જ એનર્જેટિક, એકદમ જુસ્સાથી અને ફૂલ ઓફ કોન્ફિડન્સ તમે ઘણું બધું સારું કર્યું હશે, વાંચ્યું હશે અથવા તો શોધ્યું હશે. સો that was reflected in your presentation. Fine, great, right? I hope more students would be inspired, more students will come forward for the next presentation. હવે પછી કદાચ હર્ષનો ટર્ન છે, હર્ષ, હિતિકા, if I am not wrong.
Ma'am, me, then
Yes, ma'am.
Suraj, then Hitika, then Meet.
અચ્છા અચ્છા, ફાઇન. પણ આપણે હવે નેક્સ્ટ ટાઈમ કન્ટિન્યુ કરીશું. આર્યનનો ટોપિક પૂરો થયો આજે. નેક્સ્ટ ટાઈમ થી સેકન્ડ ટોપિક કોની પાસે છે?
Ma'am, me, Harsh.
હર્ષ ને? હા, યસ હર્ષ. સો વિલ બી સ્ટાર્ટિંગ ફ્રોમ યુ નેક્સ્ટ ટાઈમ. ઓકે,
Okay, ma'am. Okay, ma'am.
થેન્ક યુ સો મચ એવરીબડી. મજા આવે છે છોકરાઓ આવી રીતે?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
ઓકે ફાઇન, ચલો બાય બાય, ટેક કેર એવરીવન. થેન્ક યુ સો મચ.
Thank you, ma'am.
મેમ ડિવિઝન સી માં પણ આ પીડીએફ મોકલાવી દેજો ને.